Okay, so good afternoon. Today is the last day of the class. So um, as I expected, unfortunately, I won't be able to cover all the material on file systems. We'll do what we can today, and then for the rest of the material, I will link to lectures from previous offerings. Which should cover all the slides for file system and also reliability. Um, I think I removed reliability slides from the schedule, but you can find the slides on the GitHub repository. Okay, so we talked about two observations that we have. And so let's jump into where we left off from the last lecture. So we are going through a bunch of definitions before we talk about the first file system in this lecture. So one of the definitions that we have to go through is the definition of directory. I'm gonna assume that you know what directories are from ECE 252, but very briefly, this is a directory is basically a file that contains other directories or other files. So it's a recursive definition. The root directory in Linux and in Unix systems is usually the symbol that you can see here. So this is your root directory. Now there are two different paths in the system. So there's an absolute path which gives you a human readable name to your particular file from the root directory. And there is a relative path from a particular directory to the file that you want to access. So it just assumes that you're giving address from a particular directory. So let's say if you want to do a relative access, address to this foo.txt residing in SMZ directory, which resides in home directory, which resides in the root directory. Let's assume that we want to produce a relative path from home directory. Then we just go from SMZ to foo. This should definitely be familiar to you from ECE 252. Now there are two types of links. There is a hard link and there is soft link. Hard link is basically another name for the same file. If you delete one of the names, then that name gets deleted, but the file remains. The only situation that you can, the only condition that you can delete the file is if there is only one name to that file. And in that case, if you delete that one name, then you can delete the file. So in this particular example, let's assume that there are two names for this file. There's this usr lib foo and there is usr lib7 foo. Let's say you delete the second one, just that name gets deleted, but the first one will carry on the file. Now, this is different with soft links. So let's assume this time that one of these two links are soft link. Let's assume that this guy is a soft link. Then if you delete the hard link, the original name, what happens is that the file will be deleted and you will end up with a dangling pointer, a name that points to nothing. So again, this should be familiar to you from 252. Just a reminder, directories are files. They're stored as files, and you could potentially use all the system calls that you use to access files. You can open them, you can read them. However, writing to a directory is usually protected. You cannot write to a directory file. Now, to modify directory files, there are certain system calls available. For example, you can create a new directory. You can create links. You can unlink. So basically, although they are files, although directories are files in nature, we have a specific system call interface to manipulate them and modify them. Right, so I don't exactly know if these were covered in ECE 252, but these are the functions, for example, in libc that you can use to manipulate directory files. The second definition is a volume. So what is a volume? Volume is a logical storage. To support the logical storage, you can use multiple physical storages or storage resources. For example, you can buy a 2 terabyte hard disk drive, or let's say 5 of them, and then create a 10 terabyte volume from this. Now, why is volume something that we should care about? The reason is because each file system can only be installed on a single volume. Now, if you have 2 or 3 or more than one volume with their own file systems, there is a way to connect them, and the way to connect 2 volumes is called mounting. So when you mount a volume to another volume, you make the file system in the second volume accessible in the first volume. So let's look at an example. I think the example is clear enough. Let's say you have a USB device. This is a single physical storage, and let's assume that you formatted it, you created a single logical volume, and let's assume that you have installed a file system on it with formatting it, and you have a bunch of files on your USB device. Now, let's assume that we have Alice's laptop and Bob's desktop. Each one of them has its own file system. Let's assume that we mount the USB device to USB 1 file. So this is a single point, a single address, root volume USB 1. So that's the address. And we then mount the USB volume to this file. In Alice's laptop and in Bob's desktop, we mount it to root media disk 1. Now, by mounting this to Alice's laptop and Bob's desktop, we make the file system in our USB device accessible to the host file system in Alice and Bob's machines. Now, if you follow, for example, this, if you want to read root volume USB 1, movies, then vacation, the MOV. So if you enter this address in Alice's system, the host file system recognizes everything all the way to USB 1 So this is all defined in the host file system. The host file system realizes that this point is where the second file system is mounted. So then it uses the rest of the address to pass it to the second file system to then search for this file within its file system. The same with Bob's system. There you're going to be using with a different media. Oh geez. Then disk one. Then movies, and then vacation. So again, all the way to here is recognizable in Bob's host file system, and then from here till the end, you can send it to the second file system. I just noticed that there are 2 questions here that I missed. So are we responsible for the slides until the end of reliability for exam? No. So everything that I just covered in today's lecture will be covered in the final exam. The rest is just, if you are interested, you can watch the lectures from previous offerings. But it won't be asked. You won't be asked about them in final exam. How does a file system relate to paging? So file system manages your permanent storage. With paging, sometimes you want to save some of the pages. When you evict a page, you want to save them in your permanent storage. So at that point, you're talking to your file system and you're asking your file system to permanently store the content of a page. So that's the point where you talk to the file system to save a page. And when you want to bring back a page that you have saved in your permanent storage, you want to read it in your memory, then again, you're going to communicate with file system. You're going to ask file system to grab the data for a particular page. You know in which file you have stored it. So you just say, from this file, give me these particular bytes corresponding to this page. And that's how demand paging relates to file system. It's just we use the file system to save and read our swapped files as our swapped pages. Okay, now for the rest of today's lecture, we're going to focus on 2 main tasks. The first one is we're going to be given a name, a human readable name, and we're going to use the directories to turn this name to a single file number. So that's the first part. Part 1. Part 2, we're going to be given a number, and then we're going to go and find the storage blocks associated with that file. Now, this is part 2. Part 1 is easy and straightforward. Part 2 is where you have all sorts of different file systems, as we'll discuss. Okay, let's focus on part 1 for now. So to have part 1, we're going to map each human readable file to a file number. So we're going to have a mapping of file names to file numbers. each directory is also a file. So for each directory, I'm going to also have a file number. Now, let's assume that this SMZ directory in home directory, in root directory, has two directories, SE350 and ECE350 directories. So each one of them has to have its own number. And then let's assume that I have also a file in my SMZ directory called foo.txt. So this also has its own name, its own number. So basically in each file, in each directory, I'm going to be storing a mapping between names and numbers. Now, how do I find the file that I'm interested in? Well, you can recursively start from your root directory, which is a file by itself, and then search your way through your name to find the file that you want. So here's an example. Let's say that we're searching for home smz foo.txt. The first thing we're going to do is to open the file corresponding to root directory. So let's say we open this file. Now this file is corresponding to the root directory, and it's going to show us any subdirectory in the root directory. Now, which one we're interested in? We're looking for home. So we search through this file to find the record home. And by finding the record home, we'll find the file number for home. Now that we have file number for home, we can then go and open that file. So we open file 119. And now this time we're going to look for SMZ. Again, we search, we find SMZ, we find the file number for SMZ, and we open that file. Now, in SMZ, we're looking at foo.txt. So we search this file, and we find the record that we're looking for foo.txt. And this gives us the final file number, 158. Then we open that, and we have the file that we're looking for. So, okay, so searching is just a recursive call. How do we store the data in our directory files? So in SMZ, for example, SMZ directory is going to correspond to a single file. This was the file 110. So how do we structure this file? How do we store bytes in this file? One simple implementation is to just implement a linked list of all the records in SMZ. So we can start with all the directories, and then at the end put all the files. So in this example, if you remember, SMZ had SE350 and ECE350. In any Unix operating system, the dot and two dots correspond to the current directory and the parent directory. So in essence, the current file, the dot is going to be mapped to 110, which is the same file. And let's say we came to this one from 119, so that's the parent directory. And then we have the two directories. We can put some free space for future directories that we might have, and then we start our files. So overall, the data structure that we are using to store these pairs in our directory files is a simple linked list. So this is end of file. Now, this is a simple design. and it would be fine if you have only few items per directory. However, this would cause a lot of performance inefficiencies if you have thousands or hundreds of thousands of files or subdirectories in each one of your directories. Then for a single search, you have to go through you could potentially go through your entire linked list. To search a file, for example, you have to go through all your subdirectories to then start your file. So searching in this is hard. Whenever we have hardship with linked list, our second option is tree. So that's what happens. So in most file systems, in XFS, in Microsoft NTFS, in Oracle ZFS, and in so many other file systems, the way directories are stored is through a tree. Now, here I'm giving you an example of a BStar tree implementation. If you are not familiar with BStar trees, please take a look at your data structure. Just refresh your mind, your memory. I assume that they talk about BStar trees in data structure courses. If not, there are plenty of resources available online. But in essence, a BStar tree consists of a root node, and a couple of childs, and at the bottom there are leaves. Now, usually BFB plus trees are searchable with numbers. So here we're searching for a human readable name. So somehow we have to turn this name to a number. One way is to use hash. So we can hash the name to get a number. Once we have a number, we can search in our BStar tree. So usually each node has a couple of numbers stored in it. So in this particular case, I have 4 numbers per node. Now you compare your number with the first number in your list. If it is less than that, less than or equal, then you follow that link for that number. If it is more, then you go to the next number until you find the number that is greater than, greater than or equal the number that you're searching. So in this case, we're searching for 30. The first one is greater than or equal, so we follow the link. This takes us to a child. Now again, we look at the first element of the child. Again, it's greater than or equal, so we follow it to another node. In this particular case, this other node is a leaf node. It could be a multi-level, so it could be another child, but eventually you get to a leaf. Now in this leaf, you find all the hash values that are less than 58 with their file number. So in particular, let's say I was looking for this 30 for my foo.txt, and this points me to the pair of file number and file name. So foo.txt in this example is mapped to 871. Okay, so what is the benefit of this? The benefit of this is that the search is log n. So if you have n items in your directory, n entries, the search time is log n. In the linked list implementation, the search time is O of n. So we have reduced the search time dramatically. Now, how do we store this in a file? So how do we store this, file, this tree structure? One way you could do it is you can. So the first part is similar to the linked list implementation. You have just your pairs for each file and number, you put them one after another, so you just list them. So this one is the same with the flat implementation. Now you need extra room to store your B star tree nodes, the nodes that we use to search for particular pair, and these guys could just come one after another. Again, each one of them is going to have a list of numbers and list of pointers. So this point could point to another child. This could point to this child. This could point to another child. So anyhow, the rest of your file basically becomes the tree data structure. So we're storing more data in our files, in our directory files, but this gives us a benefit that is searching is faster. Okay, so we're done with this first part. So this is part one. This was pretty easy and straightforward. So we talked about searching, which is recursive. We recursively search for whatever we're looking for. We also talked about data structure. So searching algorithm, that's recursive, and then the data structure. For data structure, we saw a linked list implementation. We also saw a B star tree implementation. Now, this part, as I said, is very straightforward, and many file systems share the same design. There is not much here to be done. Now, the part that is exciting and interesting and complex is the second part. Once you find your file number, how do you find the blocks corresponding to the file number that you're looking for? So that's the interesting part. Now for this, we have to locate basically the blocks for each file. That's what we want to do. The question is, how big is each block? So this is one design choice that you have to make. How big each block should be. The smaller the block size, the more number of blocks you will need for each file. The other question that you always have to answer is, how do you find free blocks? How hard it is to find these empty blocks in your storage? How could you best preserve the locality of your data? So if you have a big file, you probably want the blocks that you use for your file to all be sequential in your storage. For example, this is very important if you have a hard disk. We saw that, right? Because each block is going to be represented by a bunch of sectors. And if you have sequential blocks, you're going to have sequential sectors. So it's important to make sure that your file is mapped to sequential blocks, so that it's mapped to sequential sectors, so that reading from your file is reading the storage for your file is fast. And finally, the reliability is important, right? So it's the reliability of your file system. Let's say you created a file, and in the midst of creating a file, or you're creating a directory, and in the midst of creating the directory, you experience a power outage. The state of your file system might then go to an undefined state, and that could compromise the reliability of your file system. So making sure that your file system is crash tolerant and crash proof is important. The first file system that we're going to talk about, and I don't know if I will get a chance to talk about, I think I will have some time to talk about another file system. So we're probably going to see two file systems today. The first one is FAT. It's the file allocation table. Now, I'm going to have a redundancy here. I'm going to say FAT table. I know that FAT has table at the end of it, but sorry for this. It's weird to just say FAT. So somebody is asking, is a storage block just a physical page? No. A storage block is mapped to, so if your storage medium is hard disk, it's an HDD, then each storage block is mapped to one or more sectors. If your storage medium is a flash drive, if it is an SSD, then each storage block is mapped to a bunch of one or more flash pages. So a storage block is completely different from your main memory pages. So main memory pages are separate from a storage block. Storage block is a unit of data that your file system deals with. Page is the unit of data that your operating system uses for memory allocation. So one is memory allocation, one is the storage allocation, and they're different. Okay, so FAT file system was introduced in 1977, so it's very old. It was initially used for floppy disks. I don't know if you've seen one in your life or you worked with one. These guys were very famous when I was a kid. So the computer games would come with these floppy disks. That's what I remember. And then if you go and we didn't have USB cards, so we had these floppy disks. You would store data on them and then take them to somewhere else. It was interesting. Anyhow, but then they're widely used file systems anywhere now. You can actually potentially format your SSD using FAT file system. Now, when you just a reminder, what we wanted to do was we wanted to get a file number and then find the corresponding storage blocks for that file. Now with FAT, it's pretty straightforward. Whatever your file number is, you come to your FAT table and you look at the entry for that file number. So if your file number is 31, you look at the 31st entry in your FAT table. If your file number is 10, then you look at the 10th entry of your FAT table, and that would give you the first block. So the 10th block in a storage would be your first block for file number 10. If file number is 100, it means that block 100 in a storage is the first block for this file. So first block is always easy to find. First block is your file number. That's pretty straightforward. So basically, this is your storage. You divide it into blocks, and for each block, we're going to have an entry in FAT table. Now, when I get a file number, I look at the corresponding entry, and that gives me the first block of my file. So, okay, I found my first block. What about the rest of the blocks? Now, the rest of the blocks are just a linked list. So once you have your first one, you look at that entry in your FAT, and then it's going to point to the next one. And next one is going to point to the next one. So you're going to have a linked list of FAT entries, and each one of them points to the next block. And that's how you can find all the blocks corresponding to your file. So you get the first number, your file number, that gives you an entry point in FAT table and gives you your first block for this file. And then following the blocks in your FAT table, you find the rest of the blocks. Each FAT entry is 32 bits. 4 bits out of these 32 bits are reserved, so we can't use them, but the rest of the bits we can use them. And as I mentioned, each file is represented as a linked list of FAT entries. Each FAT entry has a pointer to the next one. Okay, now just a quick question. How many FAT entries yeah, I guess I'll get to it later. Okay, so let's continue now. So file number is the index of the root of the block list for each file. This is what we talked about. Unused blocks, unused storage blocks can be easily found by free FAT entries. So we can just mark free FAT entries as unused. So these would correspond to free storage blocks. Now, if you want to append a new block to your file, it's easy. You find the last one, you find a free entry in your FAT, you mark it as used, and then you create a link to this file. And that's how you can grow your files. Deleting them is also easy. So if you want to delete file 31, you start with entry 31, you mark it as free, then you follow it, mark it free, you follow it, mark it free, you follow it, mark it free. So you basically free all those entries corresponding to your file. If you want to create a new file, you again search for a free entry. Once you find a free entry, this becomes your first block for this file. So at this file, if this first block is block 63, then your file number becomes file number 63, because there is this one-to-one mapping from the first entry to file number. So where do we put the FAT table? We can store it on the disk, and when you boot up your system, you can bring it to memory. What happens if you format your disk? So when you format your disk, if it is a deep format, then you just make every FAT entry free. You could also go and write 0 to all your storage blocks. If it is a quick format, then you can just make your FAT entries marked at 0 without without changing your storage blocks. So as long as your fat table is every entry there is free, then you're fine. So what is the most significant advantage of fat that has made it so common? It's simplicity. It has an extremely simple design. So it's easy to find free blocks, right? You can just search through your table, and you can search your table from where you are. So the last time you search your table, you can keep a pointer and then search for the next block up or down from where you are right now. It's very easy, as we saw, to append to your file. It's very easy to delete your file. All of it implementation-wise is absolutely easy. Now, what are the disadvantages of FAT? So the first one is this simplicity comes with a cost of performance cost. And as we will discuss, it also comes with security and reliability costs as well. But let's first talk about the performance cost. Let's assume that you want to seek to middle of a big file. Let's say you have a file of 2 GB and you want to seek to the second half of your file. This basically means that you have to go through your first block, your second block, your third block, and then you have to search through your linked list until you find the block that you're interested in. So searching through the blocks of your file is order of the number of blocks in your file. So that's expensive, right? Especially if you have a large file, then you have to search through it, and that's order of n if you have n blocks. The second thing about this is poor locality. Now, as you append to your files and delete certain blocks of files, and append and delete and append and delete and create new files and so on and so forth, you get fragmentation, right? Here, fragmentation, by fragmentation, I mean you get some empty holes in your table, and then once you append to your file, you lose sequential blocks for your file. You end up spreading your file blocks throughout your FAT table. For those of us who are old enough to work with operating systems that use primarily FAT file system, every once in a while we had to do defragmentation. So here, let me search defragmentation of disk. So yeah, so this would be something that looks very familiar. What happened? I guess the picture that we were seeing, this one with, yeah. So the picture I remember seeing a lot is this one in Windows. So gosh. Yeah, so I wish I could make it bigger, but as you can see, these white spaces are the empty space, and as you can see, it's a spread all over. So if you, for example, if this is the state of your disk, and at this point you create a really big file, then that big file is going to be a spread through all these holes. So the blocks associated with this file are not going to be sequential. And if they're not sequential here, they're not going to be sequential on the hard disk, for example. So then if you end up reading this file in once, the read performance would be absolutely slow. So after a while, when your system would get to this state, you would do a defragmentation. And when you do a defragmentation, your operating system or your file system could try to make sure that by moving data around, first of all, make sure that all these empty blocks are at the, for example, end of your fact table. So all of them are in the same place, so that if you want to create a big file, you have a whole bunch of free spots next to each other. It would also try to potentially move the blocks for commonly used files to be close to each other, so that the performance of reads would be good. Now, after a defragmentation would take a long time, but then once you were done with your defragmentation, the performance of your system would jump to a higher level for a while, until again your system gets fragmented, and then you would need to do another defragmentation. The other disadvantage of FAT was lack of support for hard links. In fact, there was no metadata the FAT file system did not think about reserving a metadata for each file, and that plus the fact that the entry to your file was a single entry in your FAT table led to lack of support for hard links. The other thing about it is the limited storage of both the volume and also the size of a single file. So a size of a single file in FAT file system was 4 GB. So if you have a file that is bigger than 4 GB, FAT file system cannot support it. And the size of a volume is 1 TB. So you cannot have a volume that is more than 1 TB. So this is actually the harshest thing about the most limiting factor of FAT. You cannot support, like if you buy a SSD that has, I don't know, 2 TB, then half of it you can't use. And again, we really today have files that are more than 4 GB, so that wouldn't work with FAT file system. There are other extensions to FAT that would try to address some of these issues. So that's possible. You could potentially use the extensions of FAT. And finally, security and reliability was bad. There was lack of support for access rights, and also the reliability of the file system. Okay, so how much time do I have left? Okay, I have 30 minutes, so I can cover another file system. So the second file system we're going to talk about is called FFS, a Berkeley Unix Fast File System. So it originally was so obviously, given the name, it was developed at Berkeley, and so I don't know if I want to cover this or not, because this is where I ended SE 350, so I didn't talk about fast file systems. But I guess I do have 30 minutes time, so. Yeah, I guess I will cover this. If it was like 10 minutes, I would have said, let's end the lecture, but it's like 30 minutes. Okay. Okay, so the concepts that we're going to see in FCF in FFS is the inode and then inumber. So inumber is the file number that you have, and it's used to index into inode array. So each inode has multiple level of indexed structure. So the same pattern that we saw for directories. Initially, the first one that we saw was a linked list of file name, file number entries, and then we said that was bad, and then we talked about tree structure, B star tree in particular. We actually saw this pattern when we were talking about page tables as well. So initially we talked about a flat representation of page table, and then we said this is not good, so we're going to use tree. Now the same thing is going to happen here. So in fact, the representation of files is with linked list. So we have a flat representation. We're going to change that to tree. So that's basically where we're going with this. Free space is going to be managed with bitmaps. We'll talk about it. Okay, so similar to FAT, the concept here is called inode array. So you have an inode array, which has which is an array of inodes. Now each inode is, as you can see it here. So each inode has some space for file metadata. So this is an attempt to make FAT better. Obviously, FAT didn't have much metadata, so here we are. We're putting some metadata as first class entity in our file system. Then we have a bunch of pointers. Now, in each inode, you get 12 direct pointers. So each direct pointer points to a single a storage block. You have one indirect pointer, which points to a block that points to two blocks. Not to two blocks, sorry, to a bunch of blocks. And then you have a single doubly indirect pointer, which, as the name suggests, it points to a single block. This single block points to a bunch of blocks. And then these guys point to a bunch of blocks. So you have two levels. And then a single triple indirect pointer, which points to a single block, which points to double indirect blocks, which each one of them points to indirect blocks. which then point to a bunch of blocks. So 12 of these, one of single, one double, and one triple. Now let's talk about these. So the metadata, you can use it to store every metadata that you could think of. The user, the group, access control, and so on and so forth. The direct pointers, each one of them points to a single block. Let's assume that each block is 4 kilobytes. Then with these pointers, you can cover 48 kilobytes. So if your file is smaller than 48 kilobyte, all it takes is to use as many direct pointers as needed to store your file. Now, obviously, not all of our files are 48 kilobytes. So if your file is bigger than this, then you, a flashback, this shows you what they were thinking, right? Most of our files are here, small. So this Inode structure will cover them all. So it will cover majority of our files here. They could all fit in by using some of these direct pointers. That would be enough to cover them. Now, with indirect pointers, you can cover majority of big files. So we studied this, we discussed this, that you could have a lot of big files. You could have a few big files, but then they're big, so they're going to consume a lot of storage. Now, this is our attempt to cover them as well. Now, each block is 4 kilobyte. So they could cover 1,024 pointers. Assuming that each pointer is 4 kilobyte. Sorry, each pointer is 4 bytes. Then a storage block of 4 kilobyte consists of 1,024 pointers. So with the single indirect pointer could cover 4 megabyte, right? Because this points to a block, and this block points to 124 other blocks. Each one of them is 4 kilobytes. So this would be 4 megabytes. Now, the second one, the doubly one, is an order of magnitude larger because it has 1,024 of the indirect pointers, and each indirect pointer can cover 4 megabyte. So 4 megabyte times 1,024, that's 4 gigabyte. So that's how much we can cover using these two. It's going to be 4 megabyte plus 4 gigabyte plus 48 kilobyte. Now the last one is a triple, so it's going to be having 1024 of the doubly ones, and each doubly one covers 4 gigabyte. So in total, the last one covers 4 terabyte. Now, each inode is going to represent a single file. So what is the maximum size of a file? Well, the maximum size of a file is 48 kilobyte plus 4 megabyte plus 4 gigabyte plus 4 terabyte. So this is the maximum size of a file in Berkeley file system. Compare this to FAT. The maximum size of the file in FAT was 4 GB. Here we have added an extra 4 TB plus some small amount. We talked about metadata, we talked about direct block, indirect block, doubly indirect blocks, and triply indirect blocks. Okay. So FFS basically ends up being like this asymmetric tree, as we saw. So there are the, you know, the small files will be a shallow tree, right? Just one level of indirection. Medium-sized ones would use maybe 2 levels, and then extremely large files would use 3 levels of indirection. Now this is good because we can also in our representation of files, we can save, if, for example, if your file is small, you don't need to use the pointers. If your file is big, then you can use those pointers. Okay, so here are some examples. So how many access for a block 5 do you need? One, right? You just look at the indirect pointers, and that takes you to the file that you're interested in. Now, what if you're looking at number 23? Then this would be a 2 access, because the first 12 ones are indirect, but then this is number 23, so this is going to be in the second one, so you have to first access the 1 level pointer, and then from 1 level pointer find the corresponding number that you want. What about 340? So you can just see that this is going to be requiring 3 accesses. You access the first one, the triply pointer, the second level, the third level, to eventually find your data block. This the Inode Array. So this FFS, a little bit of history. FFS was really optimized for HDD, for hard disk drives. They did so many smart things to make FFS work fast on HDDs, on hard disk drives, on magnetic devices, because, you know, the magnetic storage was very common at the time that FFS was introduced. So there are so many different optimizations that have been implemented in FFS, at least the original version, for this magnetic disk storages. So here are a few of them. There are more, but then here are a few. So usually the inodes were stored at fixed locations in the outer circles. So for example, here you can see these are where the inodes were stored. And this would be at the format time, right? You would create these guys for your inodes. So in the early days, there was just a single, let's say, single inode, and then this would be bad because you would have to first read your inode to see which blocks are used for your file. So let's say you have file number 20. You first go to your inode array, you find inode 20, you open this inode, and then you read here to see where your file is. Then your file might be here in inner circles. So the head should first come here and then find where it should go and then come here. So a lot of movements to find your file and then fetch the corresponding sector for that file. In later versions, they realized that that was bad, so they divided the disk into groups, and then for each group they put an inode, so that all the files that are here in these tracks, their inode is here, so that you read the inode and then your file is here. The head doesn't need to move much. And if your inode is here, then your file is here. Again, you read the inode and then you can find your file within that group. The head of the disk doesn't need to move much. The same here. So this was an optimization they did. They also reserved some space for when most of your groups become full, and then you don't have enough space. Then you could use that space for that situation. Now, how do you find free blocks and use them? So you could have a simple bitmap of all the blocks in your hard disk drive, and then all the ones that are used, you mark them as used, and all the ones that are not used, you mark them as free. Now, if you want to find, then you just search through this bitmap to find the blocks that are empty. Now, this would be so how you find your empty blocks, you could use different algorithms very similar to the one. So in this idea of using bitmaps and then searching for the free blocks is common everywhere, right? Even you did it for memory allocation for heap, and then you implemented first fit, and in fact first fit actually works well with this, because you could you could keep all the free. So if you're using first fit for small files, you're gonna end up filling your bitmap at the beginning of it, and then most of your free blocks will be at the end of your linked list, because every time you're allocating, you're doing first fit. So you're starting from the beginning of your list and finding holes. So you will end up keeping this all these empty blocks at the end. And if you have a really big file, that comes handy, because most of the free blocks are at the end. You can use them all for this big file that you want to allocate and write. So I got a question here. Why does block 340 use a double indirect block if indirect blocks have 1024 pointers? Wouldn't block 340 just need an indirect block? It's a good question. I'll go back. So 5 is 1, obviously. 23 is definitely 2. Now, my guess is this is a right, so 1 to 12 are here. Then this guy is going to cover yeah. So first of all, this is block. I believe you're right. So this might be a typo in my slides. So yeah, I will. If this is wrong, I think it is wrong. I think this is a typo in my slides. It might be lacking a 0 here. Then I'll correct myself in Piazza. I will put a Piazza post correcting this. Good catch. So we talked about that. So if it is, so let's finish up with FFS. So it's an efficient storage for both the small and large files. Locality is kind of preserved. If you have a small file, then it really doesn't matter. If you have a big file, then with the way that we use first feet, then there's a high chance that you can get empty blocks at the end of your list, and then get locality. It also preserves metadata, and it also does so this particular is correct for HDD, as we discussed, having groups and then putting inodes next to your data, preserve locality for your inode and your data. You don't need to do defragmentation, so this is a plus. Now, it's inefficient for tiny files, right? So if you have a file that only has 1 byte, each inode has a lot of bytes, right? Because it's kind of like you have a template for your file, and if your file is just few bytes, then you're wasting a lot of storage to just store this 1 byte, because you have all your I mean, metadata is fine, but then all those indirect and direct and doubly direct and sorry, all the direct pointers, indirect pointers, doubly indirect, and triply indirect pointers, all of those are extra if you have a small files. Right, so sorry. The other thing about this is that if your file is mostly contiguous in your disk, again, your representation of your file is inefficient, right? Because you're using all these pointers to point to all these files that you're storing, whereas you could potentially just store 2 entries, like what is the first block, what is the last block, and that would be enough. If you have a big file that is contiguous from block 10 to block 10,000, you can just store this information, which is actually something that is stored in the Microsoft file system. So instead of storing all these intermittent pointers to all the blocks that you want for your file, you could just store 2 numbers, the first block and the end block, if you have everything is contiguous. So this basically is very rigid. Sorry, this is very rigid encoding for your files. It doesn't allow you some optimization in case where you're lucky and you can save your file in a contiguous region. And this optimization also is costly. The optimization that the file system does in keeping some of its storage reserved for when the file system is full. FFS also has some iterations and some extensions. The one that we saw here is pretty much the basic one, and just the main idea behind it. How much time do I have? Okay, I don't have any time left, so I'm going to stop here. So thank you so much for sticking around. This was the last lecture. Again, I will link to lectures from the previous terms for the rest of the slides, and also reliability. This wouldn't be necessary for the exam, of course. So exam will cover everything that I covered in the lectures, not the links that I'm going to provide. Now for the exam, try to be ready for all the questions in your quizzes. So I'm gonna just turn quiz questions to exam questions, right? There will be some true falses, some multiple choices, some explanations, and some questions about scheduling, questions about address translations, and so on and so forth. Try to read Berkeley exams and also SE 350 exams to just get a sense of how the final exam will look like. I will try my best. I haven't designed the test, but I will try to make it easy because I also don't want to spend that much time grading them. So hopefully it will be a win-win for everyone. Yeah, that's pretty much it. So somebody's asking, do you teach future courses? I think at this point I'm scheduled to teach distributed systems in I think 2023. I don't know. I think it would be your fourth term. I don't know, but you might. At least at this point, I'm scheduled to teach distributed systems, but we'll see if I end up teaching it. Yep. So that's that. Thank you so much. Take care, be safe, and then this is the last. I may come to the exam, I don't know, but if not, then oh, if you have questions, shoot me an email, post on Piazza, or you could, if you want to meet with me, just send me an email. We can figure something out. Take care, be safe, and bye.